So in this question here, we're going to find the inverse Laplace transform of this function here, s divided by s squared minus 4s plus 5. Now, what I've done previously, I've factored out our denominator and then break them apart into partial fraction decomposition. Now, s squared minus 4s plus 5, we don't have that luxury. We can only solve for s by using the quadratic formula. So we're going to need a different technique in order to do that. So breaking my f of s into p of s over q of s. That's something I always like to do with these style of questions. And then I work with each part individually. Here, p of s is just s, so that's pretty straightforward. So at the moment, I'm limited to what I can do here. But my q of s, I'm going to let that equal my denominator, which is s squared minus 4s plus 5. Now, what I can do here in normal terms with quadratics, I can find the square. So let's just do that. So s squared minus 4s, that becomes s minus 2 squared, and then minus 4 plus 5. So as in I've gained an extra 4, that's what the minus 4 is. And then I just simplify that off as s minus 2 squared plus 1. So now my f of s will now become s over s minus 2 squared plus 1. Now, when we've got this kind of format in our denominator, there is a couple of standard Laplace inverse transforms that we can apply, and hopefully we can manipulate this equation somehow and get to use them. So the first one is c times s minus a over s minus a squared plus b squared. Now, c is a constant, a is a constant, and b is also a constant. Now this one will give me c times e to the a t cosine of bt. So here, take the square root of b, that will give me my input for my cosine, and my a here, that will go with my exponential function. So here we've got a combination of exponential and cosine. Now it's something you see very often when solving differential equations, which is where we're going to be going eventually with some of these videos on these inverse Laplace transforms. So that's what we've got there. So now that's one version with the cosine. Now there is another version which uses sine, and that is c times 1 over s minus a squared plus 1. That would give me c e to the at sine of t. Now I've left a gap there because what can happen here, I can copy this one at the top with cosine as a result inside it and change my 1's to b squared and then a b, and then my result will then become sine of bt. So what I want to do now is try and manipulate this equation, try and get a result where I can use these formulas. So let's just do that. So f of s equals s over s minus 2 squared plus 1. Now I'm going to write that 1 as 1 squared, because 1 squared is 1. We're not changing anything. That's going to help me then to recognise these in my function here for my standard Laplace inverse transforms. Now what I want here, to use this one, I want s minus a. So here my a is 2. If I was to use that format there in my denominator, forget the numerators for the moment, and my b will be 1. And c, my constant, I don't know what that is yet because I've got to manipulate this and try and get it into these kind of formats. So what I could do is, I've got an s minus 2 squared here. I want an s minus 2 to copy this format to get this kind of general result. So if I put in there s minus 2. And then what I do is, because I've put in a minus 2 to get this, what I need to do now is add 2. So if I add 2, I've then got the same value for my f of s, but I've also now got an s minus 2 squared and s minus 2 for this format. I've got my b squared, which is a 1 squared, but now I've only got here a 2. So we're sort of there, but there's still a bit more to do. But first things here now, what I can do is I can break this function apart. So this will now equal s minus 2, I'll leave that in the brackets, come to this bit in a moment. So I can write this as s minus 2 squared plus 1 squared. So that takes care of breaking the fraction apart with this bit. And now add 2 over the same denominator. So that's what I've got breaking it apart. So now I've got something I can work with. So I can definitely get a result like this one. All I need to do now is manipulate this bit to try and get a result like this one. Now 2 here, what I could do, I could rewrite that as a 1, put a 1 there, and then multiply the whole thing by 2. So if I put my plus sign there and bring the constant out to the front, I've got 2 times 1 over s minus 2 squared plus 1 squared and a 1. I've now got something that looks like this one. So this looks ready now for my Laplace transform. So here for my constant c, just to be sure, here on this one, for this one, here my c is just 1. So c1 would equal 1. But here I've got b s minus a squared plus b squared. I've got s minus 2 squared plus 1 squared, so my a is 2, b is 1. That's good. But I've also got a constant here now, which is a 2. So for this one, my c would be 2. So here I've got my second constant is 2. So now I'm ready to go straight in and take my inverse Laplace transform of this. So let's go for that. So now my inverse Laplace of f, that equals, well, this one, I've got a is 2, b is 1, and c1 is 1. So I'll just go straight in with an e to the at. So I've got e to the 2t. And my cosine, that will be b times t. So it's just going to be 1 times t, which is just t. So that's taking care of this one. And then on this one, I can add, I've got a constant which is 2 for this format. So now I've got 2. And then c, that's my constant, e to the at, so e to the 2t again. And sine of b times t, b is 1, so now I've just got sine of t. And that is my inverse Laplace transform of my function here, f of s. So that's our result. Okay.